Something in this room knows that I'm here, and unless you know it's Achilles' heel, there's no way to bypass its 8 sensors. This is my most recent project. It's a fairly small security device that's built around the ESP32S3 module. This chip has built-in Wi-Fi and Bluetooth connectivity, and is more than capable of interfacing with all of these sensors. This microcontroller also has less than a milliamp of sleep current, which goes down to about 100 microamps in deep sleep. This ESP chip is capable of communicating through Wi-Fi, a home server, or other services like IFTTT, but I'm hoping to integrate this board with Home Assistant. Anyways, let's get started straight away with the most interesting elements, the sensors. So there are two, technically three motion detectors. First of all, there's this time of flight sensor, which is a fancy way of saying distance sensor. This sensor can measure accurately up to a distance of 4 meters at a 50 Hz polling rate. It also has a programmable region of interest with a max FOV of 27 degrees. All this means is that there's no way to walk past this sensor without being seen. There's also a more advanced IR presence and motion detection system. This chip has the same 4 meter range and is capable of distinguishing between stationary objects and moving objects. But most importantly, it has an ultra-wide FOV of 80 degrees and is sensitive to 5 to 20 micrometer wavelength of light, which just so happens to be the wavelength emitted by the human body. This essentially makes it an ultra-wide thermal camera. The third, technically motion sensor, is a slide sensor. It isn't anything fancy at all, but it can detect when a light switch has been flipped, a container has been opened, or when a shadow passes it. It can also be used with a laser for ultra-long range line break detection. By simply checking how quickly the light values change, the alarm can be sounded. Only when there's an abrupt change from light to dark or dark to light, an alert can be sent. This approach is much better than having a single light threshold, as it can work during the day and night. It also filters out slow changing environmental light changes. For example, this sensor is completely unaffected by clouds, sunsets, sunrises, and other disturbances. For the clever clogs among you, a threshold value is defined by calculating the absolute value of a derivative of the light data. Anyways, there are also ways of detecting motion without sight. There are two accelerometers. Well, there's supposed to be two, but they're not soldered on. Just ignore that, pretend like they're still there. One of these is a basic 3-axis accelerometer, which is used for low-power periodic polling. And this big one here is a more advanced IMU, but it gets activated when the ESP wants more accurate and precise data. This large accelerometer can detect 3D linear acceleration, rotational acceleration, and has a 3D digital magnetic sensor too. These accelerometers make it possible to detect when the sensor itself is being moved. This makes it especially useful to mount this on a door or have a sensor be hidden away, in a location where it's going to get moved but it's not going to get seen. There's also a Hall effect sensor that can precisely detect the motion of a magnet from quite an impressive distance, especially if the magnet is powerful. Finally, there's a read switch, which isn't too precise, but it can be used as an incredibly energy efficient interrupt. If all of the sensors are completely disabled, the sensor can go into deep sleep mode until this read switch is triggered. This means that the sensor can be idle for around a month without needing to recharge. Now finally, there's a temperature sensor. It's mostly for monitoring purposes and integration of a thermostat system. This isn't actually related to any security, but it's nice to have on a wireless sensor board. Wait, before we continue, I'd like to point out this video's sponsor, JLC PCB. JLC PCB is an easy, reliable, and affordable PCB manufacturer. I've been using JLC PCB even before any sponsorships, and I can really recommend their products to both beginners and more advanced engineers. JLC offer basic 2-layer boards for less than $5, but also specialized in advanced engineering-grade PCBs even with component assembly. JLC also offers specialized PCBs such as aluminum or copper core, flexible PCBs, and their new flex heater boards. Currently, JLC PCB are offering a $30 discount on their 6-layer PCBs with free V-in pad. Another cool option offered by JLC PCB are inspection reports, production images, and even X-rays. Simply export your Gerber file, drag it into JLC's instant quote page, and go to checkout. The whole ordering process is easy and quick, and your order will have live updates showing you the PCB's progress. I also want to showcase JLC's transparent PCBs. These boards are extremely underrated and are shockingly cheap. These also flex and cost less than $25. Check out the link in the description for JLC PCB, and new registering customers will get $123 of various coupons to help you start your projects. Alright, now for the output. There are these individually addressable LEDs, but unfortunately these only work with 5 volts, and 5 volts is only present when a USB cable is plugged in. This was simply because I couldn't find any good individually addressable LEDs that work at 3.3 volts. There are still RGB LEDs that work on 3.3 volts, but they're analog and do not use digital input. There are also a few LEDs scattered around the board just for debugging. Over here there's a port to output power, a port for 2 GPIO pins, and 2 different I2C channels, one coming straight out of the ESP and one which connects to an I2C multiplexer. These I2C connections allow you to attach extra sensors such as a MEMS microphone, a capacitive touch sensor, or a 24 GHz human detection sensor. The sensor is actually really cool because it can detect people's exact position in 3D space, track micro movements such as breathing or heartbeat, and even sense through walls and around corners. Anyways, at the back you've got a JTAG connection, which can be routed out, but in 99% of all situations you don't actually need a JTAG connection, so these can simply be used as GPIOs carrying whatever signal you'd like. Right, so this is the development board for the ESP32S3. Notice how it has two USB ports? This is because this chip can be programmed with both USB and UART. On my board I only have one port, so you might be wondering, which one am I using, USB or UART? Well, it's both. I've combined the USB ports into one. I'm using a very small digital switch to change between the two programming types. By default, the USB is connected to the UART converter, but by pressing the switch, the UART is disconnected and a direct connection is made between the port and the ESP module. By the way, this chip here is for ESD protection. You can actually see this chip being reused everywhere on the board, pretty much in every output. This stealth mode switch here disables all the diagnosis and status LEDs, except for the battery charging one. This saves power and makes sure this module is as discreet as possible. This LED turns on only when the battery is charging. It's off when there's no battery installed, and it's off when the battery is full or discharging. Speaking of stealth mode, this whole PCB is black, not flashy, and can be idly left around, hiding its function in plain sight. Alternatively, you can 3D print a nondescript enclosure for it, like I have done here. So if you want to be the opposite of stealthy, there's also a buzzer array at the back. But you can always connect the ports to a much larger alarm system. And if you're wondering what this whole area is about, these are just two 3.3V power supplies. One rail is used to power the ESP and sensors, while the other is used for LEDs and buzzers. This one's actually directly connected to the stealth mode switch. There are also some more random components scattered around the board, for example this resettable fuse and some other protection chips. This here is actually an ideal diode, which removes the 0.6V drop you'd get if you passed the input power for a regular silicon diode. This adds reverse polarity protection without the downsides of a diode. There's also an adjustable analog input here for setting a custom threshold, setting a sensor polling rate, or whatever you'd like. There's also this user definable button and two buttons used for programming. At the back there may be one or two jumpers and pads. Well, there are quite a few, but all of these serve a purpose. These either bypass components, change digital addresses, adjust hardware config settings, toggle features, or route out signals. Oh, and something I forgot to mention about the battery. This sensor board isn't designed to run on the battery alone. Primary supply is the USB, and the battery is mostly a backup or a short-term solution. I haven't actually tested this yet, but in regular operation, I'd guess this battery can only supply power for about a day or two, unless you're disabling loads of the sensors. This is going to be handy if you want to quickly set something up, like let's say you're leaving for work in the morning and you have an electrician coming to your house unsupervised. If you're leaving for your holidays for a couple of weeks, this should definitely be plugged in. This battery automatically charges when the USB is plugged in, and when the cable is disconnected, the battery seamlessly takes over. So you might be wondering what this project's Achilles heel is. You know, its fatal flaw, and that'll be Wi-Fi connectivity. This sensor must always be connected to Wi-Fi to send any data across. I did find one janky workaround to get a portable mode working. When the sensor's triggered, an LED can barely start to blink. In theory, this is a good idea as you can tell if a sensor has been triggered or not, but in practice, when you check on the sensor, you will trigger it. You will almost certainly trigger it too when you're arming it. I suppose Bluetooth could also be another solution to get portable mode working. The Wi-Fi reliance is also fatal for power outages. While a backup battery can keep this thing running, any sent data will simply not get picked up. This board does also have a very rudimentary wired communication. This chip here is a signal inverter for GPIO21, so you can route out a differential signal which should be able to reach a few hundred meters. You are limited on speed though, since there's no dedicated differential pair driver and no buffer for GPIO21, the inverted signal will ever so slightly lag behind the data being sent from a GPIO. This isn't a problem for slow speeds, but it seems like issues start to crop up at communication speeds above 20 kHz. Now let's address these three components. These aren't soldered on because these chips just barely exist, and JLC PCB quite literally had zero in stock. These archaic chips are only available on breakout boards, and these two could be sourced from Adafruit. My order was actually about 10 times the cost of these chips. Anyways, this one here had to be ordered from a dodgy reseller in China, so when you're designing boards you should always double check that your components are actually in stock. Anyways, let's stop beating around the bush, let's attach your components and let's code this thing. Shit, these two components are correct, but they're the wrong package. Fuck. Oh, by the way, this black component here is a bulk tantalum capacitor. It has the same ratings as this case E capacitor, but at a much smaller size. Anyways, when the sensor first starts up, it'll do a quick self-test and then pair to Wi-Fi. When everything is successful, the lights will flash blue and the sensor will be ready to arm. If there's no Wi-Fi, these LEDs will flash red. Once you are ready to initiate the sensor, just press this button and it'll start reading the sensors. Instead of using Home Assistant, I found that integrating a Discord webhook is far simpler, more reliable, and completely free. I also have integrated modes. By default there are 8, and these can be cycled through by holding the button. So when one of these sensors picks up an anomaly, it'll send a message to a Discord server. And this is what setting up looks like from start to finish. And there we go, that's all. There are also these 3 booleans that can be set in the IDE. Software Stealth is a software-controlled stealth mode, but does not rely on the physical switch. I will mention skip arming time shortly, and Rapid Startup bypasses non-critical checks and tests to make sure the sensor runs in a couple of seconds rather than around 10. One more thing, if there's a brownout in your power supply while you're away, the sensor will not get stuck in the waiting for button input stage. If a button is not pressed for 10 minutes, the button press event will be bypassed and the sensor will auto-deploy. Skip arming time bypasses the 10-minute arming period and makes sure the sensor immediately starts running upon receiving power. There's also Wi-Fi outage detection and automatic reconnection, and finally the mode is stored in the ESP's non-volatile memory, so brownouts don't reset the operating mode back to 0. And you might be wondering, why did I make this niche board and what am I going to use it for? Good question. Anyways, thank you for watching, and if you've enjoyed the video and want to see more like this, make sure to subscribe and drop a like. I will see you next time.